analysis of bivariate data. So if you record the observations on two set of variables, say indicated by x and y or x1 and x2, then that data is called as bivariate data. And again, we observe here the points as n pairs of x comma y. So the observations recorded will be indicated in small letters. The capital letters indicate the variables. I can treat these two variables as individual variables, and you can obtain all the descriptive statistics what we have discussed till now. And along with that, one wishes to study what is the effect of the increase or decrease in one variable on the other variable. So which leads in if at all we say that one variable is affecting the other variable, then we could see to what extent it is affecting. And if I know a particular value in x, what will be the particular value of y? So that is called as the mathematical relationship between x and y. Those things could be easily determined. And this comes under the category of analysis of bivariate data. So here we mainly discuss about two cases when we have bivariate data. First case is whether there is any relationship between x and y exists. So is x and y related? So whenever we say that x and y is related, only then I can see that a change in x will influence a change in y or vice versa. So a relationship must be uh, verified. So an establishment of the relation should be checked, and we call about the mathematical relation, and it comes to the mathematical relation, we call it as function. And the general way to write a function is, say, x is equal to f of y or y is equal to f of x. And this could be any function. So we could talk about a straight line function, or we could talk about quadratic function, a logarithmic function, exponential function, etc. And when we talk about the simplest form of the relationship between two variables, we say the simplest relationship is linear relationship. Linear relationship indicates a straight line relationship. That is, you have your bivariate data, and if you plot your xy and observe that most of the points are around imaginary straight line, in that case, we say the data is linearly related, and this plot is called as scatter plot, and that is one of the basic tools available in the field of statistics to check whether any sort of relationship exists in the bivariate data. So we'll look into this scatter plot in detail now. So basically, it is just a plot of points, and the reason why it is called as scatter plot is that we observe the points scattered throughout the xy plane. So you have your bivariate data. So you'll take suitable scale for x and y axis, and you will mark the points x comma y as you did in the frequency polygon case. X and f mark ಮಾಡ್ತಿದ್ರಿ, ಅದೇ ತರ x and y ಇರುತ್ತೆ ಇವಾಗ ಅದನ್ನ mark ಮಾಡಬೇಕು. And you could observe any sort of relationship or a behavior relationship. And of the cases, the simplest form as said is a straight line. So if you could somehow observe that, it's not perfectly straight line. We are not interested in joining every pair. We are, somewhat, we are modeling on an average what the relationship is. So you could have the data such that it could be a non-linear case like this. It could be a cubic equation or a non-linear equation. So this also may be approximated using the straight line. But what happens is that there is much error observed here rather in the previous case. And the error is said to be the mathematical error, which is nothing but the distance between the actual value and the whatever the relationship you are using to determine that is called as the estimated value. So whenever there is much error observed in the pattern, then we say the line is not a best fit. So usually when you say you're talking about a relationship, we first do a scatter plot analysis and check whether a straight line could be used in order to predict or in order to analyze the behavior of the data. And if your data is not, following along a straight line, then we say the relationship to be non-linear relationship or a curvilinear relationship. Now, to make the thing simpler, so here we talk about a simple relationship, which is nothing but the linear relationship. And mathematically, a linear relationship is generally given between two variables, and the form of the relationship is y is equal to mx plus c. So you might have studied this in your 10th or 11th, 12th standards. So this line, straight line y is equal to mx plus c indicates, two quantities here. So you have a straight line in your xy plane. This straight line is making some angle theta, and that is, represented by, slope. M is equal to slope, which is called as tan theta. And the point where your line, straight line, is touching the y-axis, that point is called as the c value of c, which is called as the y-intercept. Y-intercept and the where your straight line is touching y. Now we are using this concept of straight line in actually studying whether there exists a straight line in our bivariate data. If so, we proceed further and try to obtain what are the values of this m and c. And if my line is a best fit line, that is, it is, we are observing minimum possible error. In that case, the line could be used in estimating the future values. Now let me make you understand these things with an example. So you have, say, the observations recorded on two variables, say age, or maybe let me talk about, say, the amount of a particular food item or a particular nutrient, whatever it is, and then you're recording the values of blood pressure. So you have selected some 10 random patients, and then you are accessing the data, what type of food or a particular nutrient they have consumed, the amount, especially you are recording that, and then you are recording their blood pressure values also. So maybe, say, on a particular day they had around, say, 0.2 mg, 1.5 mg, and maybe 2.6. Some might have not consumed that on a day. So you'll record that particular nutrient value. So you have various experimental techniques where, or you could, you can come up with techniques where how you can measure this particular variable, and then you will record the values of blood pressure, maybe 78, 85, 73, 93, 94, and so on. Now you want to, make an analysis, or you have a assumption that an increase in the consumption of this nutrient will decrease the blood pressure, or a decrease in this will increase the blood pressure. So you have to come up with cause and effect relationship between the two variables. Then you have to see the influence of the variable on each other. So you have to see whether your increase in x is showing an increase in y or a decrease in y, or a decrease in x is showing an increase in y or a decrease in y. So there should be some relationship. So x increases, that implies y is also increasing, or you could have x increasing, that is implying that y is decreasing. So this could be one case. On the other hand, if I say, so if this is the case, I say x is influencing y. So we say y is dependent on x, and you can control this variable x. So you can control the food intake, the nutrient value, your diet could be controlled so that this can be easily monitored. So in this, I'm trying to establish a relationship as what will be the value of dp when I'm consuming x units of this nutrient so many times, and these are some of the mathematical constants which could be easily estimated. On the other hand, my variables could be such that I'm talking about a case where my y is influencing the value of x. So an increase in y will indicate an increase in x or a decrease in x. A decrease in y will indicate an increase or decrease. So whenever you collect a bivariate data, only one suitable relationship could be observed. So there could be several cases. You could observe only one possible relationship. That is, An increase will lead to increase or a decrease will lead to decrease. Now the question is how to identify whether they increase is causing increase or decrease is causing decrease. If you have very small number of observations recorded, you could actually see what is happening from point to point. Now if you look here, my first value of x is 0.2, it got increased to 1.5, got increased to 2.6 and so on. So my y values are also increasing. So an increase in x is leading to an increase in y, and if that happens for most of the data cases, then I say my x and y are behaving in a uniform way, or I can say in one direction, and that direction is increase lead to increase. On the other hand, if you are recording or observing the value such that the increase in x is leading to decrease in the particular value, in that case, I could say an increase in x is leading to decrease in y. So I say x and y are behaving in the opposite direction, or they are moving in opposite direction. Now this data now could be easily plotted in order to observe what is the type of straight line or the set of scatter points what we are observing. So I have some values, blood pressure values. So I'll take a suitable scale. So I'll have say 80, maybe 84, 88, 92, 96. I'm taking 4 units. Similarly, you will have some observations, say 0.5, 1, 1.5, 2.53. So these are the scale values of your x. Now mark the pairs of observations. First one, I have, so I'm taking this as x and y. So I have x is equal to 0.2 with y is equal to 93. And then I have x as 1.5. I have y as 91. And then I have 2.6 and 86, which is somewhere here, and then 2.7 and 80. So you will get a plot like this. So this is called as a scatter plot. So if you have many such values, you could observe the points scattered throughout your xy plane. Now you see whether there is any straight line behavior happening in the data. Now, of all the possible scatter plots, we could categorize them into 6 cases. So I could have a scatter plot. So I have just interchanged the axis here, but usually we'll take x values on x-axis, y values on y-axis. Now, even if you swap your x and y, the graph doesn't change. You can observe that. Instead of taking this here, so if I, inverse them, exchange them, then the graph doesn't change. So the behavior properties are kept as it is. And the first kind of scatter plot, which is very rare to observe, is a perfect relationship where an increase in x is leading to proportional increase in y, or a decrease in x is leading to proportional decrease in y. So whatever the quantity you observe an increase in y, the proportional changes are observed in y. In that case, you will observe the alignment of points perfectly on a straight line, and we say the relationship is perfect. And if it is making an angle, or if you see that this is the increasing part of x, this is the increasing part of y, so increase is leading to increase. So it is making an acute angle with the x-axis, or you could just say that the straight line goes from the bottom left to top right. In that case, we say the relationship to be positive relationship. And this is the case where, see, we have an increasing value of x, which is leading to decreasing value of y, or an increase in y is leading to decrease in x. So in this case, we say the relationship is negative. And as said, we are looking into just the simple relationship, which is straight line. And statistically, this relationship is observed to be, or simply called as, correlation. And in more technical terms, it is called a simple correlation because we are only dealing with 2 variables. So you can have the cases where you could talk about multiple correlation also, where you are recording more than 3 variables or 3 or more variables. In that case, you could talk about multiple correlation. Now, correlation simply means the amount of linear relationship. or the degree of linear relationship. So we are suspecting a straight line relationship in the data. To what extent they are related by a straight line relationship, that measure or that number is called as correlation. So basically it is a unit free measure, and one such method of observing the correlation is scatter plot. We indicate this correlation by the symbol R, small letter R, and I could say that my R is equal to +1 here, R is equal to -1. So can observe this value only if each and every point observed is on the straight line. Even if single point or more points are just clustered around the straight line or outside the straight line, the value of R will, increase 1 minus 1, and it will decrease from +1. So it basically lies between -1 and +1. Now this is the possible two cases. So case 1, you could have a perfect positive correlation. What is perfect positive correlation? Perfect positive correlation is the case where every increase in X is leading to proportionate increase in Y. Perfect negative, a proportionate decrease in X is leading to proportionate decrease in Y. So let me show an example. So I'll take some data. So I have X and Y. So I have X value, say, increasing at a pace of 10. So X is increasing at a pace of 10 units. Now I could have the data where my Y is increasing proportionately by 1. So a change in 10 influences a change by 1. And both are, the relationship is such that an increase is leading to increase, and the change is also proportionate. So again, X increases by 10, Y increases by 1. X increases by 10, Y increases by 1. So such situations are called as proportionate increase. So this could be another such data. So when you try and plot this data in a scatter plot, you will observe the points always falls on this category of the scatter plot, where every point is aligned on a straight line. Now, even if one value doesn't follow that behavior, now X is increased by 10, but instead of Y increasing by 2, it has just increased by 1. So I'll have that point slightly away from the straight line, which leads to the third category of scatter plot, where we say most of the points are aligned on the straight line, but one or two are just clustered around the straight line. In that case, we say R is very high, but it is positive. So positive indicating greater than 0 indicates positive here. And if you have most of the points clustered around the straight line, then we say R is very high. If you observe the case where you have a possible straight line to observe, but much of the points are far away from the straight line, though we say R is positive, but the amount of correlation will be low. Why it is low? Because I have many data points which is not following the mathematical rule of straight line. So it is away from the straight line. So if you just look into the cluster of points without straight line, it is easy for you to assume any function or any other curve other than the straight line. So in that case, we say R is low. And if you are imagining a straight line in this direction, we say R is positive. If you could imagine a straight line in this direction, we say R is negative. Similarly, when it comes to the perfect negative correlation, a decrease in your X will lead to proportionate decrease in Y. Your X is decreasing by 5, and say Y is increasing by 1. So as said, negative correlation happens when your variables move in the opposite direction. So X increases, Y decreases, or Y increases, X decreases. In that case, we say the correlation is negative. If a unit change in X, or a proportionate change in X or uniform change in X leads to uniform change in Y, in that case, we get all the points aligned in this direction, and the straight line, which you can imagine for that cluster of points or scatter of points, is that it is starting from your top left and it is moving to the right bottom. If any of the points doesn't follow this, but they simply, decrease, then I could have cluster of points around the straight line. So in this case, we say R is negative, but it is high because most of the points are around the line, around the straight line. So this is the case when you have negative correlation, you will have the points scattered on the, far away from the straight line, far away from the straight line. So these are the possible categories. Now sometimes, as said, my correlation is only about linear relationship. I could have a relationship between x and y. So if you are familiar with the quadratic functions like parabola, circles, or nonlinear equations, so this is a second degree relationship between x and y. So I have points observed such that my data is in a curvilinear behavior. So though I could say I could fit a straight line in this direction or this direction, whatever the straight line you pick, in most of the cases or in almost all of the cases, many points are away from the straight line. So this is indicating no straight line relationship, which is mathematically called as non-linear relationship. There exists relationship between x and y, which is a non-linear, but we are interested in only linear relationship. So hence, even though there exists a relationship here, we say correlation is equal to 0. No correlation. The reason for that is our correlation talks about a straight line relationship. Any relationship other than straight line, we say correlation is equal to 0. At certain times, your data plotted on your x and y or scatter plot could be such that it becomes very difficult you to assume or imagine a straight line. Now, in that case, we say the points is scattered throughout the xy plane. So you can say, I can imagine a straight line like this or like this. So many such possibilities will be there. But every straight line what you imagine is producing much of the error. So even in that case, we say there is no relation at all. X and Y are not related at all. They don't behave in a straight line. They don't behave in a curved line. They don't have any mathematical relationship. Whenever we have, say, X and Y do not have mathematical relationship, then we say X and Y are independent. So when I say x and y are independent, I could have a logical explanation. That explanation is your x is increasing, but that is not having any influence on y. So the increase in x is not increasing y, is not at all decreasing y. Or if you say that my y is increasing, again that is not having any effect on your x to be increasing or decreasing. So a change in one variable doesn't lead to change in another variable. In that case, we say x and y are independent. So this is the very basic method of analyzing the correlation, and that is called as scatter plot. And if you look into the merits and demerits of the scatter plot, it is very easy to construct for a given bivariate data. You can easily see what type of behavior or what type of correlation exists for the data, but you cannot give the exact amount or the value of your correlation. Only in the cases where you observe R is equal to 0, plus 1 and minus 1 could be observed, provided your behavior is such that they are producing this, but this is a very rare case. So this plus 1 and minus 1 is a very rare case, but in most of the situations, you can have a 0 correlation. Naturally, when you say that I have my x variable such that it is not at all dependent between y, in that case, the influence of the effect on one is not observed on the other. Naturally, we say correlation doesn't exist. So you can take, say, the age as well as time invested in doing or eating, etc. So though you observe that, we cannot make any common, generalized statements that as age decreases, you will eat lot, as age increases, you will eat low. But, if you observe the numerical data, you could see that yes, as age increases, the human beings naturally take or they'll lessen the quantity of eating. But when you look into the time or the quantity of such variable, you need not see any relationships. Increase or decrease is definitely not influencing or getting influenced by other variables. In that case, we say correlation doesn't exist. But since we have a numerical way of measuring this correlation, if I just give you any data such as x and y, you don't know what the variables are, you can apply the formula for correlation. You will actually come up with some answer like say 0.3074 or 0.45. But if you actually look in the definition of the variable, only then you can make sense whether x and y are related or they are not related. So even in the case where you have x and y non-linearly related, you could produce a correlation like this 0.3, 0.4. But is it a significant correlation? Is it actually the true scenario for the population? So that we have to test, and we'll look into that case when we talk about the hypothesis testing. Now coming to the merits, as said, the exact value of R cannot be observed from the scatter plot, and that's why we come up with the various techniques of measuring this correlation. And one such technique is given by the person called as Carl Pearson, and it is also called as product moment correlation. So we talked about this moment in the previous class. If you remember, R moment is defined as total of your x minus x bar to the power of r over n. And I said your mu1, mu2, mu3, mu4, the first four moments are basically used in order to observe the values of mean, variance, skewness, kurtosis. So this is generally called as moments. So he uses the moments like mean and standard deviation of variance in order to come up with a formula for the correlation. So that's why Carl Pearson method is also called as product moment correlation. So here we have bivariate data. So n points or n pairs are observed. In that case, we say R is given by the simple definition ratio of covariance to the product of standard deviations. So we have two variables. For both the variables, we can compute the means as well as standard deviations. And if you compute another term on the measure, which is called as covariance, then your correlation is defined as the ratio of covariance to product of standard deviations. And we also know that standard deviation is nothing but square root of variance. So this can be simply also written in terms of variance as variance of x into square root of variance of y. And mathematically, product of the square roots is same as square root of the product. So I can just write this as variance of x into variance of y. Now coming to what is this covariance? Covariance is a simple term similar to our variance, and it is shortly indicated as COV of x comma y. We have variance. Variance indicates what is the difference between or the distance between my x and x bar. So what is the distance between x and x bar on an average? So we are looking into the amount of variation in the data or in the observations with respect to their mean. How far is the mean from the observations or how close the mean is from the observations? That value is captured by the measure, standard deviation and variance. Now we have two variables here, x and y. Now I want to see how is x behaving with respect to its mean, that is x bar. How is y behaving with respect to y bar, and what is the joint effect? What is the joint effect? Because we are talking about covariance. So we talked about variance. So this is the variance within the variable. Now we need the joint effect between x and y. So we call the average behavior of x minus x bar into y minus y bar as the covariance. Now in order to obtain it simply and to avoid the calculational steps of computing the mean, we could apply the techniques of algebra and simplify this formula as covariance is equal to sigma xy by n, minus sigma x by n into sigma y by n. So this method makes you calculate x bar and y bar, obtain the difference from x and y, obtain the product and the sum, whereas it just simply says you have x and y given, obtain the total of x, obtain the total of y, multiply them, obtain the total, then easily obtain the variance. And we also know the formula of variance. Variance is equal to square root of sigma x minus x bar whole square by n, and variance of y is nothing but square root of, sorry, when I say variance, there is no square root, y minus y bar whole square by n. So if I substitute these three basic forms of covariance and variance in the formula of correlation, I get a formula which is same as total of x minus x bar into y minus y bar. I have divided by n, and then we have square root of the variance. Variance is sigma x minus x bar whole square by n, sigma y minus y bar whole square by n. So I have 2n basically inside the square root. When I take it out, you have square root of 1 by n square that get cancels, and this is the simplified form of the correlation. Now again, if you want to save the computational steps, you can expand your x bar and y bar using the formula sigma x by n, sigma y by n. And I have also given you the simplified form of the variance, which is sigma x square by n minus x bar square. So using these shortcut methods, so I could come up with a formula which is very easy to obtain numerically, and that formula is n sigma xy minus sigma x sigma y divided by n sigma x square minus sigma x whole square into n sigma y square minus sigma y whole square. Please write the squares and the bases correctly and take down these formulas. As said in the previous class, I'll be showing the working on all the categories. You solve some problems and see which method is easier. And the topics what I'm talking today, they come under chapter 16, block 4 of your book. And if you are representing the first PUC book, you can go through chapter 6. And if you look into your book, so this formula is used in computing the correlation. Again, to further simplify the notations, they have just used x in the place of x minus x bar, and they have used y in the place of y minus y bar. So how you can question me how you can use x and y? I said they are just the notations. So I could say that if you are indicating your original variables x and y in capital letters, obtain the difference or the deviations of x from x bar and deviations from y bar and indicate them in small letters, then you can simply write your correlation as sigma xy minus square root of sigma x square into sigma y square. So this happens only if you have already subtracted your x from its mean, y from its mean. Otherwise, if you are dealing with your original x and y, you have to use this methods. And all these methods are called as direct methods of computation of your value of r. So memorize this formula, you memorize this formula, and one question for 5 to 10 marks numerical problem will be there on the Carl Pearson or the product moment correlation. You can have it for up to 10 marks. Okay, so please make a note of the formulas. So I'll take a problem and I'll show how we can easily compute the value of r. square ಸ್ವಲ್ಪ neat ಬರ್ಕೋಬೇಕು, especially the term in the denominator. So I have n sigma x square minus sigma x whole square, and the same terms with y. So this is indicating total of x square. So we'll compute x square first and we'll record its total. This is the total of x whole square, sigma x whole square. So there are various other methods of computing correlation also based on the type of the data. As said, if you are dealing with a completely continuous set of variables x, y, z, then you could easily apply the method of Carl-Pearson. But as we know that the means and the deviations have a tendency of getting affected by the extreme values. So as far as possible, try to look into the data and apply this formula, especially Carl-Pearson, when you don't have extreme values in the data. As said, now the question what we have to do when you have extreme values. If you have sufficiently larger set of observations, try and remove those extreme values. Otherwise, go and use the other techniques where you can easily obtain the correlation though you have the extreme values. And one such method is by the rank method, which was observed or given by a person called as Spearman's correlation. Spearman, he calls it as Spearman's rank correlation. So here what we do is, if we have some extreme values in the data, we'll not use the original data, but we rank the data. So we'll have set of x values, set of y values, assign ranks for x either in increasing or decreasing order, and do the same thing for y. And then by using the ranks, you can compute the correlation. Now your ranks doesn't get affected much by extreme values. So you have whether the largest value is 100 or 1 lakh or 1000, the rank will be the maximum. So if you have 5 values where 100 is maximum, so that might take rank 1 because that is the highest. So if you have 10,000 in the data, that will also take rank 1. So your ranks doesn't get much affected by the extreme values, so that you could have a correlation computed based on the ranks. Okay, so these are the various techniques of identifying whether there is any